So first, I would like to thank Professor Lions and the organizing committee for the kind invitation. It's really of my great pleasure and honor to give this talk here. So today I'm going to talk about striated regularity of 2D inhomogeneous incompressible Navier-Stokes system with variable viscosity. This is joint work with Mathématiques from Université de Bordeaux. Let's first recall what it means, this inhomogeneous incompressible Navier-Stokes system. So first we have this conservation of mass. We have this conservation of momentum. We assume the fluid is incompressible. Here this rho denotes the density of the fluid. V denotes the velocity of the fluid. Pi is a scalar pressure function which guarantees this divergence precondition of the velocity field. Here this mu of rho denotes the viscous coefficient, which is usually a non-decreasing smooth function of the density. This m here is a symmetric part of the Hessian of the velocity field called a stress tensor to this problem. So for this problem, say first let's assume this mu rho equals some positive constant. This system has the following basic features. Like due to the divergence precondition of the convection velocity field, we have this conservation with LP norm of the density. Also, this distribution function is conserved for all time t greater than 0. Also, we have this energy law, and we also have this called a scaling invariance property. So which means if this rho v pi is a solution to this inhomogeneous incompressible Navier-Stokes system, and if you scale this rho v pi in this way, you'll find that this rho v pi lambda t of x is again a solution to this inhomogeneous Navier-Stokes system. This scaling invariance leads to the notion of called a critical regularity, which is the minimum regularity required by the initial data to have this system has a unique local solution. So based on the energy law, Lajinskaya and Strelnikov proved in 1975 in bounded domain with Dirichlet boundary condition for the velocity field. In 2 space dimension, they can prove the global well-postedness. In 3 space dimension, local well-postedness. And for small data, also they have global well-postedness. And again, based on the energy law, when we assume this viscous coefficient equals some positive constant, this global existence of weak solution was proved by Enseignement in 1990. So the general result of this global existence of finite energy weak solution with variable viscosity was presented in chapter 1 of Professor Liang's book on incompressible models in 1996. So to talk about the next topic, we needed to recall you this definition of breadth of space. So we first have this function phi, which is supported on this annulus, and we can, with this phi, we can define this dyadic operator delta JA, which is a frequency cutoff operator such that the frequency of A is supported on annulus, radius of which is like 2 to the power of j. This I learned from Jean-Yves long time ago. So with this dyadic operator, you can define this breadth of space, have this derivative of S, and the P denotes the integrability, and R means the summation with respect to the indices of J. In the case when S less than 0, we have the following alternative definition for this breadth of space through this heat semigroup. So in particular, if R equals plus infinity, this definition can be written like this. So in particular, this tells you as long as A belongs to this breadth of space with negative indices, the heat semigroup involution of A should decay like t to the power of s over 2 as t tends to infinity. So this definition will give us motivation for this time-weighted energy estimate for this inhomogeneous, incompressible Navier-Stokes system. So in this situation, one always assume this initial density is bounded away from 0. So instead of this rho v formulation, you can also formulate the system as A and V. A equals rho inverse minus 1. So as this formulation for rho and V, you'll find that the system for AV also has this scaling invariance property. So when you assume the initial density is not far away from 1, Denshun first proved with initial data in this critical space, and when this A is sufficiently small, then he can prove local well-postedness of this problem. And when P between 1 and 2D, even for variable viscosity, with the critical norm of the initial data to be sufficiently small, Abidi proved in 2007 this problem has a global solution, but the uniqueness was only proved for P between 1 and a D. And even with different inequability index for this inhomogeneity, the velocity with PQ satisfies some condition such that this Q is sufficiently small and P is large enough. In this situation, they can also prove the global unique solution. So the endpoint result in this direction is by Danshan and Muha in 2012, where they can prove with initial A0 belongs to this multiply space of this space of space and to be sufficiently small, and V0 to be sufficiently small in this space of space, then they can prove this system has a unique global solution. So in particular, it's easy to check when P is between 1 and 2D, this space of space B of dot D over P, P1 is a subspace of this multiply space. So in particular, this result solves this uniqueness issue, which was left open in this paper by Hamadi Abidi. On the other hand, motivated by my study with respect on 3D anisotropic Navier-Stokes system, where we only require the horizontal components of initial velocity to be sufficiently small, we can prove similar result for 3D inhomogeneous Navier-Stokes system. In this situation, this inhomogeneity, which satisfies this transport equation, serves as one component of the initial velocity field. So as long as this A0 and V0H to be sufficiently small, compared with the exponential V03, we can still prove this system has a unique global solution. But after this result, we began to build example which satisfy this Monist condition. It turns out it's not so easy. So in order to build example which satisfies Monist condition of this type, joint work with Zhang, we prove with A0 in this isentropic space and V0 in this anisotropic space with similar type of Monist condition, we still can prove global well-postedness result. So the novelty of this paper is like this isentropic structure of this A0 and this anisotropic structure of this V0 is consistent in this system due to the spatial structure of this system. In fact, it's not correct in general to prove anisotropic regularities for transport equation. That's why we have to use this isentropic base of space for this A0. And for general density in the critical space, like with the initial ρ0, has a positive lower bound, and it belongs to this base of space, critical base of space, and with the initial velocity to be small in this critical base of space, joint work with Abidi and Gulongui, we can prove the global existence and the uniqueness to this problem. And we can even prove this result with initial velocity in base of space with negative infinite indices, because here we can allow this P between 3 and 4. So in particular, this result tells you, just as a classical Navier-Stokes system, for the inhomogeneous Navier-Stokes system, when the initial density is bounded away from 0, with high oscillation for the initial velocity field, for this inhomogeneous Navier-Stokes system with constant viscosity, this problem still has global unique solution. We can even joint work with Zhang, we can even construct an example of this type, which is not small, in the base of space we just mentioned, such that this problem still has a global unique solution. So the motivation of this result is motivated by the study for the classical Navier-Stokes system by Zhang and Gallagher Isabella. So as we mentioned before, the reason why we needed this inhomogeneous incompressible Navier-Stokes system is because this system can be used to describe the mixture of several immiscible, incompressible fluid flow. So in this situation, because the mixture of different fluid, there could have interface between fluids with different density. So the more natural space for the density should be zero belongs to the bounded function space. Joint work with my former PhD student, Jinji Huang, and also with Merspek Ku, we can prove as long as even this A0 belongs to L infinity, initial velocity field belongs to this critical base of space. Under this Monnius condition, we can still prove this system has a global solution. But here, we can only allow P between 1 and dr between 1 and infinity. That's because the main tools we used to prove the result of this type is to use like the maximum regularity estimate for time involutionary Stokes operator. So because of these tools, we cannot allow this R to be 1. So because in order to prove the uniqueness issue for result like this with A0 belongs to L infinity, we needed to use Lagrange approach. So usually we needed this convection velocity to belong to L1 Lipschitz. So in order to prove the uniqueness, we need a little bit more regularity for the initial velocity field. Then by applying this maximum regularity estimate for time involutionary Stokes operator, we can prove the velocity field belongs to L1 Lipschitz space. And eventually we can prove uniqueness issue for this problem. And a similar result was proved by Zhang and myself in the upspace. So the main difficulty in this situation is because for the inhomogeneous Navier-Stokes system, the only boundary condition can be at only for the velocity field, So the main part of this paper is to write the explicit formulation for the pressure function with only this Dirichlet boundary condition of the velocity field. On the other hand, Kachkov proved in 1974 with Z0 belongs to L infinity and has a positive lower bound. V0 belongs to H1. This problem, and small, has a global strong solution, but the uniqueness was left open in this paper. So firstly, Zhang and Muha proved in 2012 with Z0 belongs to L infinity and has a positive lower bound. V0 belongs to H2. Then they can prove uniqueness. And then this problem was completely solved by this paper by Merspek Ku, myself, and Zhang in 2012. In this situation, when we assume this Z0 belongs to L infinity and has a positive lower bound, in two space dimension, we only require this V0 belongs to HS for any s greater than 0. In three space dimension, V0 is to be small in H1. Then not only we can prove the global existence of this problem, but we also can prove the uniqueness of this problem. So the main tools to prove this issue is to use time-weighted energy estimate. And very recently, I can even prove with Z0 has a positive lower bound and upper bound, and with initial velocity field in B1/2 to be sufficiently small, then we can prove this system has a global existence of weak solution. Moreover, this U should satisfy energy of this type. And that's the reason why we have the square root of T like here, because compared with initial regularity, this quantity has lost one derivative. So according to this definition of base of space with negative indices, so here we should have this square root of T. But as a result of Kachkov result here, I cannot prove the uniqueness issue for this problem. There's only existence result. So in general, for this problem with variable viscosity, the following result was presented in this book by Professor Lions in 1996, giving initial data which satisfies this quantity to be finite. This problem has a global weak solution in the sense of distribution, and in fact, for the density function, it's renormalized the solution, and moreover, this distribution function is preserved for any t greater than 0. So after this result in this book, Professor Lions listed a lot of open questions, but I'm only to mention the following two, which is related to my talk today. The first one is like the regularity of such solution in 2D is not known, not like the classical Navier-Stokes system or the inhomogeneous Navier-Stokes system with constant viscosity. So in this situation, with variable viscosity, this regularity in 2D is not known. So the second open question is listed on this book by Professor Lions on 39 of this book. Is called the propagation of regularity for density patch. Like given initial density Z0, which is characteristic function on some smooth domain. According to Lions' theorem, this problem has a global weak solution such that this density function is still some characteristic function, and moreover, the volume of this domain is preserved. So the problem proposed by Professor Lions is whether or not the regularity of the boundary is preserved by the time evolution. So in fact, the first progress is again due to this paper by Hafele-Dunsham and Moha with a constant viscosity case, because in that situation, when Z0 has a small jump across this C1 interface, this Z0 is an element of this multiply space of this Bessel space. So this structure in particular tells you if the boundary belongs to C1 and with a little bit more regularity for the initial velocity, this boundary regularity can be propagated. But it turns out not only for C1 interface, joint work with Shen Liao, we can prove similar result for any like WK plus 2P regularity for the boundary. Of course, in this situation, we need to order the tangential regularity of the initial velocity or the initial vorticity. So in order to get rid of this assumption for small jump across this interface, let's assume this initial boundary of this initial domain omega 0 can be parameterized in this way, like the length of the curve. And we assume for any positive constant, eta 1 and eta 2, if this Z0 is like eta 1 on omega 0 and eta 2 on the complementary state of this omega 0. And moreover here, we cannot prove, as Professor Lions proposed, we need a little bit more regularity. We need this V0 belongs to L2 intersect with B of dot S0 for S positive, for any S0 positive. But we cannot improve this S0 to be 0. And moreover, we need this tangential regularity for the initial velocity field. So this X0 denotes a tangential vector to the boundary, which equals like if F0 is the level set, describes the level set of this omega 0, X0 denotes this vector. So exactly this X0 is a tangential vector to this omega 0. So in this situation, we can prove the following result. With the previous assumption I just mentioned, we can prove for any constant eta 1 and eta 2, when this viscous coefficient equals some positive constant, we can prove this problem has a unique global solution, and moreover, this density should keep this structure. And moreover, this WK plus 2 P regularity of the initial domain will be preserved for all time t greater than 0. And so since here, we remove this smallness assumption for this jump, eta 1 minus eta 2, so we cannot use such tools as a maximum regularity estimate as we in our previous paper. Secondly, so the method of time-weighted energy estimate is very useful to be here. So in order to propagate this W2P regularity of the initial boundary, we need, in fact, to prove the energy estimate of gradient partial T of V. But it turns out if we do work on the energy estimate for gradient partial T of V, we cannot do with only bounded density. So in this situation, instead of estimate gradient partial T of V, we have to work with energy estimate of the gradient of dt of V. dt designates the material derivative. And then moreover, with initial density being in this bounded function space, we cannot, the previous result cannot prove the propagation of regularity, Bessel regularity for the velocity field. But in this paper, by using this property of characterization of base of space with positive index, we succeed in establishing the propagation of base of regularity of the velocity field. So after this result, there is another result by Zhang Li, who basically follow our approach of this time-weighted energy estimate even with vacuum. Because of this time-weighted energy estimate, he can prove the Lipschitz regularity of the velocity field. Then he can use Lagrange approach to prove uniqueness of solution to this problem. So motivated by our previous paper and also the paper by Benoit Duertin, Dunshan and Muha can prove the propagation of C1 regularity for 3D density patch, even with vacuum. So now let's go back to the original problem, which was proposed in Professor Liang's book. That's the inhomogeneous Navier-Stokes system, because the previous result, we always requires this mu rho to be a positive constant. But this original problem in the book of Professor Liang's is about this inhomogeneous Navier-Stokes system with variable viscosity. So in this situation, I should mention the result by Benoit Duertin in 1997, who proposed this solar energy method and a proof even with vacuum, if this U0 belongs to H1 and mu 0 minus 1 L infinity to be sufficiently small, this H1 regularity of the velocity field can be preserved, can be propagated. But this result, even he can prove this L infinity H1 regularity for the velocity. There is no uniqueness. So there is two papers. One is by Merspeko and my former PhD student, Jinji Huang, and also another paper by Abidi and myself, which basically says like with sort of a base of regularity for this mu 0 minus 1, and also it's small, then not only we can prove this existence, but also we can prove the uniqueness of such a solution. And moreover, under this assumption, we can even prove this global L1 Lipschitz estimate of the velocity field. So now, before we move to the next step, we need to borrow this definition from the book of Jean-Yves on incompressible Euler system, like this definition of non-degenerate vector fields. Let X lambda be a family of solenoidal vector fields. This solenoidal assumption is just for simplicity of the calculation. And X is called non-degenerate family of vector fields if at any point there is at least one X lambda, which the modulus of X lambda is positive. So given this non-degenerate family of vector fields X lambda, if we assume the initial velocity belongs to homogeneous negative base of space, which is to guarantee the decay of the solution, and also U0 in H1. We also need to require this directional derivative of 0 in X lambda direction to be bounded. Then under the smallest condition mu 0 minus 1 L infinity to be sufficiently small, then we can prove for 2D inhomogeneous Navier-Stokes system with variable viscosity has a global unique solution in this space. So in fact, as I mentioned, the two previous results requires the initial density to be at least continuous. In our situation, because the application of this notion of non-degenerate vector fields, we can allow initial density of this type, eta 1 on omega 0 and eta 2 on this complement part of this omega 0. And we also need to require some tangential regularity of like a directional derivative of U0 along X lambda should belong to H1. Then we can prove, as in the constant viscous case, as long as the initial density of this form, we can prove the solution should keep this structure, and moreover, this H3 regularity of the boundary can be preserved. This H3 is not critical. It is not critical. We can prove more regularity by repeating this same approach, but it will make the problem much more complicated. So the main difficulty compared with the constant viscosity is, like in the previous case, by energy method already gives you this L1 Lipschitz estimate for the velocity field. So in our situation, we will see the energy method will not provide this L1 Lipschitz estimate for the velocity field. This L1 Lipschitz estimate depends on the propagation of this tangential regularity of the velocity field. So the proof, the first step is to use like U0 belongs to L2, and U0 belongs to the sublet space with negative indices. And we can prove this L infinity L2, L2 H1 estimate. That this estimate was proved when delta equals 0 in the book of Professor Lions. But with this negative regularity assumption, we can prove the solution should decay like t to the power of negative delta, t to the power of negative delta. And here, when without this time weight, the L1 H1 estimate and also this L2 time t, L2 space with respect to ut estimate is the Benoit diagonal result. But here, with this decay, we can prove we have more decay for the gradient of u in L infinity L2. L infinity L2. But not only we can have this decay of this u of t, we can also prove for dt of u, material derivative act on u, also have this decay property. So this result, basically, we know before. But in fact, it turns out under this assumption, not only we can have this L2 space-time estimate for dt of u, we can also propagate this regularity of dt of u in L infinite L2. So this energy estimate is completely new for this inhomogeneous Navier-Stokes system with variable viscosity. But here, because we only assume this with u0 in H1. So when we propagate this dt of u, dt is basically like a second derivative of the velocity field. So that's why we have to lose one derivative. We have this additional square root of t compared with here when we propagate this regularity. So unfortunately, with this energy estimate, even with this new energy estimate, we cannot prove this L1 Lipschitz estimate for the velocity field. So in this situation, by applying this Laurent projection operator on this inhomogeneous incompressible Navier-Stokes system, you could arrive at an equation like that. You could get rid of this pressure term, and then use this divergence precondition of this u velocity field. You find this negative Laplacian of u equals the right-hand side. So in this way, inverse of minus Laplacian on both sides, and I take gradient, then you arrive at a formula like this for the gradient of u. Then by applying Gagliardo-Nilenberg inequality, you find this L infinity norm can be controlled by dt of u L2 to the square root times dt of u L4 square root. Then by using Gagliardo, once again, you find it's controlled by this quantity. Then by using energy estimate, as we already obtained, we can prove this part belongs to L1, L infinity. So the difficult part lies in the second term. This is the gradient minus Laplacian inverse, and the divergence is like double Riesz transform. And the Laurent projection operator is another projection, is another double Riesz transform. So in general, this double Riesz transform does not maps continuously from L infinity to L infinity. It's not correct. So based on an assumption of Jean-Yves in solving this vortex patch for 2D Euler system, in this situation, as long as you have one directional derivative to be good, then you can have this L infinity estimate. Because in this situation, if this two derivative here, let's assume this partial 1g belongs to W1p for p greater than 2. Then you'll find that this, for the second derivative, as long as you have this partial 1 here, because this partial 1g belongs to W1p, you have this derivative act on this, you obtain this W1p estimate. So with this W1p estimate for the high frequency part, by subleft embedding, this belongs to L infinity. So this part is good. So as long as under this assumption, As long as the second derivative, you have partial 1, you have this L infinity estimate. So the most difficult part lies on this part. When these two derivatives, there is no partial 1. That's partial 2 squared. In this situation, you have to regroup it in this way. You plus this partial 1 squared, then you find this Laplacian composite with minus Laplacian inverse. This equals minus g. And for this part, as we just explained, this part already belongs to L infinity, so we are done. So eventually, on this assumption, like one directional derivative of this g belongs to, this LP, then you could have this estimate. You could have this, you could have this L infinite estimate for this g. So then use motivated by the proof by Zhang in this book on incompressible Euler system. In general, when we have a family of non-degenerate family of vector fields, we can prove the following result for the double Riesz transform act on this G L infinite estimate. It is controlled by LP norm of G, L infinity of G, and also this directional derivative of G along this direction of x lambda. But here, compared with the proof of Zhang, because now we work in LP space, which is like Tribolt-Lizotzky type space. So we have to use maximum function properties or maximum functions to prove result of this type. Because this technique is rather technical, I'm going to skip the detail here. So this tells you, in order to estimate this high frequency part for this gradient of u, for this part, we already have the estimate. Now, with this proposition, we can estimate the second part. So in order to do this, we need to estimate the directional derivative of the velocity field along this x lambda direction. So given initial non-degenerate family of vector fields, we have to involve, as time t greater than 0, of this vector field. So with initial data like x time at the time t equals 0 equals x0, we evolve this x according to this evolution, like dt of x equals the time directional, the directional derivative of u along this x direction. And also, with this x, we need also to propagate this regularity of directional regularity of the velocity field along this x direction. So first, we need to derive the equation for Zx and ux. And because of this special property, this partial x is commutative with this material derivative. So we find immediately this z of x should satisfy equation like this. And by using commutator, you'll find a ux should satisfy equation like this with the source term. So for this equation, under some assumption, we can prove this ux have L infinity L2 estimate, and gradient of ux has L2 of t L2 estimate. Moreover, we can have this weight. Here. Here, this v of t equals exponential of c times gradient of u, L1, L infinity estimate. So this tells you, as long as you have this L1 Lipschitz estimate, you can have a global estimate of this quantity. And also, we can prove this derivative gradient u of x, this derivative regularity can be propagated. In this situation, because we have one more or less derivative, so here, that's why we have a square root of t here. But if you assume initially this u0 along this x directional derivative of u0 along this x0 direction belongs to h1. There is no singularity at the time t equals 0. So that's why you could have an estimate like this. So basically, all this estimate tells you, as long as you has L1 Lipschitz estimate, you can propagate this directional derivative of this u along this x direction. And furthermore, we can even prove this regularity of this x itself along this x direction. In this situation, we have an additional difficult term, that's pi 2, L1, L infinity. In fact, we can rewrite this pressure term of this equation to be this way, this part plus this part. This part is good. But the second part, because mu rho only belongs to L infinity, it could have discontinuity, it belongs to L infinity. So the best regularity you can expect for the second part is L1, L infinity. That's the best regularity you can expect. But again, because of this double Ritz transform, in order to estimate the L infinity estimate of this part, we need this tangential derivative of this u along this x lambda direction. So now let's go back to this problem. Then we have this Laplacian u in equal this, and then we can write this gradient of u to be two parts. The first part we can obtain by Gartley-Arthur-Dillenburg inequality, and also this time-weighted energy estimate we just obtained. So in order to estimate the second part, we use like our proposition we just mentioned. Firstly, because this P is a double Ritz transform. Use this proposition once, you get rid of this P here. But here, you still have this double Ritz transform here. So in order to estimate the L infinity norm of this part, you have to use proposition 3.3 once again. Then eventually, you arrived this gradient estimate of L infinity should be estimated by terms on the right-hand side. But fortunately here, although the right-hand side have very bad terms, we have a term here like mu rho minus 1 L infinity. This norm is preserved, is controlled by mu rho 0 minus 1 L infinity. So here, we already have this all this estimate as long as we know this L1 Lipschitz estimate of the velocity field. So substitute all the terms, all the estimate we obtained for x lambda L infinity and gradient x lambda, we eventually could have an estimate like this. Gradient of u also, we have L1, take L1 with respect to time. We achieve an estimate like this. A constant over 2 plus 1 times a known constant, which is written by this, is the initial constant, times mu rho 0 minus 1 L infinity, times exponential of the c, times L1 Lipschitz estimate of the velocity field. So because all these constants are known, are given by, controlled by the initial data, as long as this mu rho 0 minus 1 to be sufficiently small, we obtain, under this Monnius condition, we can prove this global L1 Lipschitz estimate of the velocity field. So with this L1 Lipschitz estimate of the velocity field, we can propagate this tangential regularity of the velocity field, and we can, by a routine method, we can propagate this regularity of the initial density patch. And in fact, this approach turns out to be also very useful to study elliptic equation of divergence form with L infinity coefficient. So in this situation, if we given a non-degenerate family of vector fields x lambda, and we given this elliptic system of this divergence form with this coefficient belongs to L infinity, but here we needed to also assume this directional derivative of Aij along x lambda direction to be bounded, and we also need to assume this Monnius condition of this matrix with this identity matrix. Then we can prove this system is in fact has this global L infinite estimate, could be controlled by the right-hand side, which is known already. So the main idea of the proof, just as we just mentioned, the first step, let's denote this G by this multiplication of this matrix minus identity matrix times gradient of U. So we'll first rewrite this system in this way. Because double Ritz transform maps continuously from LP to LP. So we find this gradient of U LP norm should be controlled by the right-hand side. But the LP norm of G is like this. This LP norm is controlled by this L infinity norm times gradient of u LP. So that's why we have C epsilon 0 times gradient of u LP. So as long as this epsilon to be sufficiently small, this term should be absorbed by this right-hand side term. So eventually, we can control this LP norm of gradient of u in terms of this L2p over 2 plus p norm. But in order to propagate this L infinity norm, according to what we mentioned, we also needed this directional derivative of this u along this x direction. So in this situation, again, we rewrite this partial xu system in this way, in a perturbative term. As we did before, exactly as we did before, we can prove this gradient of this partial x of u LP norm can be controlled by the right-hand side, So now, not only we have this gradient u LP norm, we also have this gradient partial xu LP norm. So with these two norms, we can use our proposition we just mentioned can be estimated like gradient L infinity norm can be estimated by this LP norm, L infinity norm, and the source term plus this part. And the G for this part is easy to obtain by using sort of a Gauss-Lagrange. For this part, L infinity norm, it's easy. And this LP norm of this part should be controlled by epsilon times gradient of u, and this should be controlled by epsilon times gradient of u L infinity. So we also have a term here and also have a term here. But all these terms we already know. The only unknown term is lines is the following term. The following lines on the following term, like here. So here, this B, this G of LP norm is controlled by epsilon times gradient of u LP. For the second term, this gradient x lambda LP times GL infinity should be controlled by epsilon 0 times gradient of u L infinity. So the idea is to use like Young's inequality. These terms should be controlled by C times epsilon times L infinity estimate of gradient u plus this known term. So eventually you find as long as this epsilon to be sufficiently small, this term should be absorbed by the left-hand side. So that's why eventually we obtain this L infinity estimate for this gradient of u. I think I'm going to stop here. Thanks a lot for your attention.